Our next topic, electrical equivalence of magnetically coupled circuits. Let us consider a magnetically coupled circuit as shown here with the two currents I1 and I2 entering at the dots. Let us write loop equations. By applying KVL, we'll get V1 of t equals to L1 di1 by dt. Since both the currents entering from the dots, mutual inductance M is considered to be a positive from the dot convention, then di2 by dt for the first loop, and for the second loop Vt2 equals to L2 di2 by dt plus M di1 by dt. We got the voltage loop equations in terms of time domain. Let us try to draw the circuit equivalent to this time domain. From this means equations, the equivalent circuit in time domain. To draw this equivalent circuit in frequency domain, the loop equations should include j omega term. Then V1 equals to j omega L1 I1 plus j omega M I2. V2 equals to j omega M I1 plus j omega L2 I2. Now these two equations represented in frequency domain, the equivalent circuit in frequency domain. Now let us shift this dot from here to here. Then we can observe that I1 is leaving the dot, whereas I1 is entering the dot. From the dot convection, the mutual flux M now becomes negative. So in this loop equations, the second term which belongs to M will become a negative. Then the equivalent circuit in time domain here will get the change in the polarities of M, negative and positive, negative and positive. In frequency domain equations also, the second term in the first equation will become negative and the first term of the second equation will become a negative. Here also the polarities changes. As the dot is shifted from this point to this point, here we got the changes of the mutual flux will become negative and the polarities also changes. Here also polarity changes. In this equation, negative includes. Now, if this dot is also shifted to this point, then both the I1 and I2 are leaving the dots. So from the dots convention, the mutual flux will become a positive. Then in these equations, M will become positive. Then the polarities of mutual flux in this circuit will become positive, negative, positive, negative. Here in frequency domain, M is positive, so these two will be positive. And then the polarities in the frequency domain equivalent circuit is also going to change from negative positive to positive, negative in both the cases. Now this dot is shifted from here to the main position. The I1 is entering to the dot, I2 is leaving the dot. Then mutual flux is negative, so in the loop equations, M will become negative. Then in the equivalent circuit, the polarities of the mutual flux is going to change. You can see negative, positive, negative, positive. Frequency domain equations, the mutual flux part will become negative. Here also it will become negative. The polarities of this equivalent circuit is also going to change to negative, positive. So depending upon the dots in the magnetically coupled circuits, the mesh equations or time domain equations is also changing. Polarities of the mutual flux is also changing, and the equations of the frequency domain is also changing at the mutual flux, as well as the polarities in the equivalent circuit is also changing. Now we have seen 4 different combinations of coupling circuits and their time domain and frequency domain equivalent circuits. Now consider this magnetically coupled circuit where the direction of I2 is reversed when we compare with the conventional figure. But you can observe that I1 is entering the dot, whereas minus I2 is entering into the dot. So the mutual flux will become positive here. As the current direction is negative, we need to submit that. Then applying the KVL for this magnetically coupled circuit, V1 of t equals to L1 di1 by dt plus the mutual flux M is positive as I1 is entering and minus I2 is entering. Then d minus I2 by dt. From this equation will become L1 di1 by dt minus M di2 by dt. This is our V1, that is the equation 1. Apply the KVL for the loop 2. Then V2 of t equals to M di1 by dt plus the self inductance L2 d minus I2 by dt. Then V2 of t will become now m di1 by dt minus L2 di2 by dt. That is equation number 2. Now, equation 1 and 2 will become mesh equations for this magnetically coupled circuit in time domain. So, let us draw the equivalent circuit in time domain. Now, from the equation number 1, if you draw, then the polarities will be L1 is positive as M1 is negative and positive here. From the equation number 2, you can see that minus L2 is considered here as a minus L2 and M is a positive one. Now, when you write these equations in the frequency domain, then V1 equals to j omega L1 I1 minus j omega M I2. Then V2 equals to j omega M I1 minus j omega L2 I2. Now let us draw the equivalent circuit in frequency domain for the above equations. This is our frequency domain equivalent circuit for this magnetically coupled circuit. This is the case where I2 is leaving the dot and minus I2 is entering into the dot. Now consider magnetically coupled circuit. Here you can see the minus I1 is entering into the dot and I2 is also entering into the dot. From the dot convention, the mutual flux is positive. But as the I2 is negative, ultimately the mutual flux term on right hand loop involves I1 would be a negative. Now let us write the loop equations. Minus V1 minus L1 di1 by dt plus M di2 by dt equals to 0. V1 equals to minus L1 di1 by dt plus M di2 by dt. That is equation 1. For V2 equals to L2 di2 by dt plus M d minus I1 by dt, which is going to give us V2 equals to L2 di2 by dt minus M di1 by dt. That is equation number 2. Now, from the equation number 1 and 2, let us draw the time domain equivalent circuit. Now, let us write the equation 1 and 2 in frequency domain. Then V1 equals to minus j omega L1 I1 plus j omega M I2. Now, from equation number 2, V2 equals to j omega L2 I2 minus j omega M I1. You can see this is a negative I1. Then here it's again negative I1. Here it is I2. And this is positive and negative minus j omega L1. This is positive and negative j omega M. Here it is positive and negative. And here it is minus. So minus and plus j omega M. This is frequency domain equivalent circuit for this magnetically coupled circuit. Now consider another magnetically coupled circuit where both the currents I1 and I2 are entering the dotted ends. Thus, the mutual flux term in both the equations is positive. From the dot convention, the polarity of V1 is reversed. Let us write the KVL equations. Minus V1 of t equals to L1 di1 by dt plus M di2 by dt. This is equation number 1. Then equation number 2, V2 of t equals to M di1 by dt plus L2 di2 by dt. These are the mesh equations in time domain. Now let us draw time domain equivalent circuit for this. So V1 negative, positive, and the current I1. This is L1 di1 by dt, positive, negative, positive, negative, M di2 by dt from the equation number 1. Now the equation number 2, let us draw this. This is I2 entering, L2 di2 by dt, both are positive, and M is also positive. So M di1 by dt, where the voltage V2 is positive here and negative here. Writing these equations in frequency domain, the first equation in frequency domain will be minus V1 equals to j omega L1 I1 plus j omega M I2. Then V2 equals to j omega M I1 plus j omega L2 I2 for equation number 2. Now let us draw the frequency domain equivalent circuit for this. I1, so V1 is positive here, negative here. Remember, the polarities are changed here for the input voltage. Then this is j omega L1 plus and minus j omega m plus minus j omega m plus and minus j omega L2. This is the current I2 given to the voltage supply V2. For this magnetically coupled circuit where the V1 polarities are reversed, these are the mesh equations in time domain, and this is the time domain equivalent circuit, this is the frequency domain equivalent circuit, and these are the frequency domain mesh equations. Now, let us consider a magnetically coupled circuit with the voltage polarities are reversed as well as the current direction of the I1 is also reversed. Let this be I1. So, I1 leaves the dot as well as minus I2 leaves the dot, whereas I2 enters the dot. Now we can consider the mutual flux MB a positive from the dot convention. However, I1 is reverse direction in the actual circuit. Hence, the terms involves I1 will be negative. Now write the KVL. Minus V1 equals to L1 d minus I1 by dt plus M d I2 by dt. Now we can write this as V1 equals to L1 d I1 by dt minus M d I2 by dt. Let it be equation 1. Now V2 equals to L2 di2 by dt plus M d minus I1 by dt. Now this can be written as V2 equals to L2 di2 by dt minus M di1 by dt. Let it be equation number 2. Then from equation 1 and 2, the time domain's equivalent circuit will be, so V1 here is the same. The current is minus I1 is entering and negative L1 d1 d2. This is M is positive, and here from the equation number 2, the same will remain, whereas M is reversed, so minus plus. Now let us write this time domain equations in frequency domain equation. Then the equation number 1 will become V1 equals to j omega L1 I1 minus j omega M I2. Now equation 2 will become V2 equals to j omega L2 I2 minus j omega M I1. The equivalent circuit will be for this magnetically coupled circuit where the voltage polarity is reversed as the current is also leaving I1. This equation 1 and the 2 are the mesh equations in time domain, and this is time domain equivalent circuit for this magnetically coupled circuit, and this is the frequency domain equivalent circuit, and these two are the frequency domain equations. Now this is regarding the different combinations of magnetically coupled circuits, time domain equations, time domain equivalent circuits, as well as frequency domain equivalent circuits and frequency domain equivalent equations. So this is regarding electrical equivalents of the magnetically coupled circuits. If this video is useful, please like, share and subscribe.